So, you want to understand the incredibly complex molecules that make up pretty much everything in our world? We're talking about everything from life-saving drugs to the fuel that powers our cities. Well, it all starts with one family, the alkanes. They are the absolute foundation of organic chemistry, the simple blueprint from which everything else is built. Just think about it for a second. There are literally millions of different organic compounds out there. How in the world can we possibly keep them all straight? And maybe more importantly, how does a researcher in Tokyo know they're talking about the exact same molecule as a clinician you'll be working with in Toronto? Well, the answer is a system. To make any sense of a huge, complex biological molecule like this one, you can't just dive into the deep end. You've got to start with the fundamental pieces, the simplest family of them all. And that brings us right back to the alkanes.
Okay, so let's get a really clear definition. What exactly makes a molecule an alkane?
It's actually beautifully simple. An alkane is a hydrocarbon, which just means it's made of only hydrogen and carbon atoms. And the key feature, the thing you've got to remember, is that it contains only single bonds. No double bonds, no triple bonds, just simple, straightforward, stable connections. We can actually boil this down to 3 simple rules. Think of it as the alkane code. Rule 1, only carbon and hydrogen. Rule 2, only single bonds. And Rule 3, they follow a really predictable formula, CnH2n plus 2. This formula works like a little machine. You just plug in the number of carbons, that's your N, and it'll tell you exactly how many hydrogens you need. So, with those rules in our back pocket, we can actually start building. Think of carbon atoms as Lego bricks that always need 4 connections. Let's start snapping them together and see what we get. Okay, so we start with just 1 carbon, and that gives us methane. Since carbon needs 4 bonds, it just grabs 4 hydrogens. Easy enough. Now, snap on a second carbon and you get ethane. They bond to each other, and then all the other open spots get filled with hydrogens. Add a third carbon, and you've just built propane. See, you can already see the pattern emerging in these simple little chains. Now, that whole building block approach is pretty simple for 1, 2, or 3 carbons. But once you get to 4 or more carbons, all of a sudden you have choices about where to put that next piece. And that, my friends, leads us to what I like to call the isomer puzzle. This puzzle has 2 main types of pieces. You can connect your carbons in one long, continuous line, kind of like a train. We call that a straight chain alkane. Or you can have a main chain with other carbons branching off of it, more like a tree. And you guessed it, that's a branched chain alkane. Let's look at a real example with 4 carbons. Check this out. Both of these molecules have the exact same formula, C4H10. 4 carbons, 10 hydrogens, but they are not the same thing. On top you have butane, a straight chain. Below it, isobutane has a main chain of 3 carbons with a little 1 carbon branch sticking off the middle. Same parts, totally different assembly. And the structural difference is huge. It actually changes their physical properties. Butane boils at just below freezing, but the more compact isobutane boils at a much colder -12 degrees Celsius. So, this leads us to the official definition. When you have compounds with the same molecular formula but a different connectivity, a different structure, they're called constitutional isomers. And like we just saw, this isn't just some random academic detail. This difference in structure creates completely distinct chemicals with totally different behaviors. So, clearly, if you have different molecules with different properties, you can't just call them both C4H10, right? That would be absolute chaos in a lab or a pharmacy. You need a clear, unmistakable naming system. You need a blueprint. And thankfully, we have one. It's called the IUPAC system, from the International Union of Pure and Applied Chemistry. This is the universal language of chemistry. Its rules make sure that a specific name leads to one and only one molecular structure. No confusion, no mistakes. And the system itself breaks down into 4 logical steps. Let's use it on our isobutane example. Step 1, find the longest chain. Okay, that's 3 carbons, so the parent name is propane. Step 2, name the branches. There's 1 branch with 1 carbon, and we call that a methyl group. Step 3, number the parent chain. That methyl group is on carbon number 2. Step 4, put it all together. 2-methylpropane, a unique name for a unique structure. Simple as that. For any of you heading into the medical or laboratory sciences, this isn't just theory. This is about safety. A precise name means the difference between giving a patient a life-saving drug and a completely different, potentially harmful substance that just happens to be its isomer. Precision here literally saves lives. Okay, so we know how to define them and how to name them. But where do we actually find these molecules? Let's zoom out a bit and look at their role in the real world. And this reveals a really fascinating contrast. On the left, we see those straight-chain alkanes as the workhorses of industry. They're the main components of oil and gas. But on the right, we see their relatives in nature. Notice how the cycloalkane molecule has its carbon chain looped back on itself to form a ring? These cycloalkanes are fundamental building blocks for countless biological molecules, including a lot of hormones and medicines. Yeah, one of the biggest roles for alkanes is fuel. They are the main thing in natural gas and petroleum formed over millions of years. In fact, natural gas is mostly methane, that very first simple alkane we built. We burn them in a process called combustion to release a ton of energy, and that's what powers our modern world. So let's bring all this together. We've defined alkanes, we've built them, we've solved the puzzle of isomers, and we understand the blueprint for naming them. But why does this first chapter matter so much? Because this right here is the central logic of all of organic chemistry. The IUPAC name reveals the exact structure of a molecule. That structure, in turn, determines how the molecule behaves, its properties, and its function. If you can master this connection with simple alkanes, you will have the master key to understanding every other family of molecules you'll ever encounter. Ultimately, these aren't just rules you have to memorize, they are the tools of creation and understanding in the entire molecular world. We've just handed you the blueprint. The real question now is, what are you going to build with it?